So we want to maximize S belong to. We only have 3 items, right? So in this case, n equal to 3. And then we want to maximize function f(x). So this is what we wanted to solve. And we start from S0 equal to empty set. Then going through the 3 steps, right? So iteration 1. Iteration 1. We need to calculate this function, right? In order to calculate this function, we need to calculate h. So, step 1. Step 1. Suppose the random permutation is, I mean, you can pick any sequence, right? It be 3, 1, 2. Okay? Python has a function called permutation, which is directly return permutation, random permutation. Step 2. So we calculate h sigma 1. Again, h sigma 1 is 3, right? So which means this is h3. This represents the third item. The third item in h, which is h1 to I minus h sigma 1 to I, sigma 1 to, so this is the 1, right? 0. So this 1 to 0 is empty set. Sigma 1, 1, right? 3, right? So h3 minus h empty set is equal to 3. So 3, let me see. So 1 is New York, 2 is Boston, 3 is DC. So 3 is 350 minus 0. Can you follow? And then h sigma 2, which is sigma 2 is 1, right? So 1 equal to h sigma 1 to 2 minus h sigma 1 to 2 minus 1, which is sigma 1, 2. 1, 3. New York, DC. 650. Minus sigma 1, 3. DC is 350. Which is 210. So please write the notes. You need to practice. Again, last homework, 11, right? Will be based on this class. For the students who only work homework assignments, right? You know, the homework 10, homework 11 will be pretty challenging. I need to make some questions difficult. Otherwise, all students will get an A, right? So which is not possible. And so h sigma 3. So sigma 3 is 2, right? So h2, which is h sigma 1 to 3 minus h sigma 1 to 2. So 1 to 3. 1 to 3 is the ground set of all cities. It's 810. I mean, this example is not in the slides. Okay, you need to write the notes. Minus. So keep in mind, for homework 11, you need to write a program to implement the steps. Okay, will be more training for you. At least, right? At least by end of the class, in the future, you can talk to people. Oh, I implement gradient descent by myself, right? I implement project gradient descent by myself, right? And then I implement greedy algorithm for submodular optimization. I implement majorization maximization by myself, right? So I hope you'll be confident to say such words. And so 1, 2. 1, 2 is 1, 3, right? 1, 3. 1, 3 is 650, which is 1, 2, 50, 0. 250. So now we have H equal to H1, H2, H3, and H1 is 2, 1, 0, H2, 250, H3, 350. This is H. So for this reason, we can write step 3, right? And keep in mind, step 3, these two are components, are constant, right? Which means in order to maximize this over S, the second and the third one can be ignored, right? Only this one involves S. So this is the reason why we need to move this S to the left. So for this reason, we have F S0 S equal to 210, 250, 350 S plus constant. Right? So that's why we want to calculate S T plus 1 equal to arc max S equal to 0, 1, 3. What is S? What S can make this maximum? See? So this is the weight of S of item 1, weight of item 2, weight of item 3. So keep in mind, right? This is equal to what? 210 plus S1 plus 250 S2 plus 350 times S3. S equal to S1, S2, S3. And then Si belong to 0 or 1. Right? So I want to maximize, of course, this should be 1, right? This should be 1, right? This should be 1, right? If you remember, right, modular maximization, we look for items, the weights are all positive, right? So the 3 weights are all positive, so we just return all items. So for this reason, this is equal to 1, 2, 3. How we say? 1, 1, 1. Right? Do you follow? So now we finish one iteration, right? And because t equal to 0, right? So this actually is 0 plus 1, which is S1. Okay? And then t equal to t plus 1 equal to 1, right? So now we finish one iteration, right? Okay, calculate h, so we can define this lower bound function, and then look for items that have positive weights. We can get as 1, and then increase step size by 1. So now we go to another iteration. Then this t becomes 1, right? So now we need to define a lower bound function based on S1, not based on S0. So now, so can I just erase this part? With this one key? So now we do second iteration. So iteration 2. So iteration 2, we know S1 equal to 1, 2, 3. So that's why we do have step 1. Decide a random permutation, right? Any random number, any random sequence. So previous one random sequence is 3, 1, 2. Now let's say maybe 2, 1, 3. 2. 2, 1, 3. And then step 2. H sigma 1. So sigma 1 is 2, right? So H2 equal to F sigma 1 to 1 minus F sigma 1 to 0. This is so sigma 1, 1 is New York, right? 250 minus 0, 50. Well, this is the empty set. And then H sigma 2. So sigma 2 is 1, right? You follow? And then F sigma 1 to 2 minus F sigma 1 to 2 minus 1, right? Which is 1. So keep in mind what? So sigma 1 to I minus 1. Okay? So you ask me how come some people can figure out such a way to calculate H, right? So this is magic for mathematician, right? I don't know how they can come out this way. So basically, if you calculate H in this way, it is guaranteed that the lower bound condition is satisfied. So 1, 2. New York, Boston. 510? Minus 250 is a 260.
Sigma 1 to 1 is just F2.
2, yeah.
Yeah,
Oh.
so.
2, what was 2?
Yeah.
2 is Boston, right?
Yes.
Oh, Boston is 300. Okay. 300. So by the way, I forgot to mention.
And 1 to 2 is also not correct.
1, 2, right? New York, Boston. It's 150,
Oh, yes.
right? So by the way, I forgot to mention, the algorithm was published at ICML. I think 2014. Okay, ICML is called the International Conference on Machine Learning, which is one of the best conferences in machine learning. Best paper award. Okay, so this was the best paper award in 2014 at ICML. And then in the same year, the author extends this framework such that it can handle conditions. Okay, conditions. And they submit the paper to NIPS. So NIPS is the second most well-known conference on machine learning. So if you talk to people, you will know SML NIPS are the best conferences on machine learning. They got best paper award. Okay. So basically say, how about we add some constraints such like some subject 2, some submodular function, let's say equal to some, for example, 3. Okay? And they say, oh, actually this framework can be extended and it can mathematically prove very good quality. But we're not going to discuss here, but I will give you some reference. And then H sigma 3 is H3, 3, right? And then F sigma 1 to 3 minus F sigma 1 to 2. So 1 to 3, 8, 10. 1, 2 is a 300. For this reason, H equal to H1, H2, H3, and H1, 210, H2, 300, H3, 300. Okay? And then step 3, which is S1 is and then we want to maximize, right? So S2 equal to arg max S belong to 0 or 1, 3, Fs1, S. And in order to find S such that this can be maximized, oh sorry, it should be plus constant. Of course, right? Because all the ways are positive. You follow? For this reason, this is equal to 1, 1, 1. And S, so S1 does not equal to S0, right? Because S1 is 1, 1, 1, S0 is empty set, right? So actually this is 0, 0, 0. But S2 equal to S1, right? S1 includes all items. S2 includes all items. So we satisfy S2 equal to S1, right? So for this reason, it converges, right? So that's why we return S2 equal to S1, so return S equal to 1, 1, 1. It's easy, right? You will be asked to implement this algorithm. So if you have any questions, you should ask now. Any question? So now, we are going to make the problem a little more challenging and see if we use the same framework or not. So now I'm going to add a constraint subject to as less than or equal to 2. So which means I want to travel, I want to visit 2 cities, up to 2 cities, such that I can pay as much as possible to the flight company, right? Maximize the flight. So based on this definition of the function, do you know what could be the 2 cities, right? Boston, DC, right? And then see if we can return the solution Boston, DC. So now let us try still we start from empty set, right? Okay? And suppose sigma is still the same, random permutation. H is the same. The only difference is subject to so which means subject to S. So which means S can have at most 2 non-zero entries, right? So that's one here. So if I say S can be at most two 1 values, so then we either pick 1 or pick 2. So in order to maximize this weight, the first one, which one should we pick? This one, right? You follow? What is the second one? This one, right? For this reason, the solution is 0, 1, 1. Right? Is this right? This is already optimal, right? You follow? And we hope next iteration will be the same, so it can converge, right? It's like magic, right? You do exhaust search, you can figure out a solution. But here, one iteration, we can get the solution. Okay? And keep in mind, right? So this is a modular function, right? You only scan each item once, you can get an optima. But here, you need to do exhaust or item set for size 1 or item set of size 2 in order to figure out the best solution, right? See, this is exponential, but this is linear. Okay? And I solve one linear function, that's one iteration, I can get the optimal solution, which is Boston DC, right? So this is very cool. So now S1 is 2, 3. 0, 1, 1, right? So S1 is 0, 1, 1. And then the randomization stays the same. And then this is the same. As well, let me see. Okay? And then this feels the same, right? So now we have S2 equal to R max S equal to 0, 1, 3 F S S. So this is the new normal function, and then subject to S. So now the question here is, let me write here. So given the h is defined as 3 values, then I want to maximize this function, pick only up to 2 items. Which 2 items should we pick? These 2, right? So for this reason, this is equal to 0, 1, 1. And then S2 equal to S1. So you converge, so return 0, 1, 1. That's the final solution. Careful? So which means this algorithm also works well even we have a constraint about the size of the final subset. So this is what I'm going to do. One question is ask you to implement maximization without constraint. Another will ask you to implement maximization with a size constraint. So two are a little different, but I mean, for the good practice for you. Okay, so we basically finish MM algorithm for submodular maximization. So now in the future, right? So if you want to maximize submodular function, you should recall either you apply greedy algorithm or you apply MM algorithm. And then you ask me which one I prefer, right? So then next part is to evaluate theoretically what is quality. So I already mentioned, right? I mean, it can return a solution that can be very close, as good as global optima. I mean, what do you mean as good as? How to quantify, right? So we have the following theory. So please write down, it's very important because I'm pretty sure in the future, right? People ask you, you want to apply greedy algorithm. I mean, how good is this algorithm, right? Then you can tell people, this is the approximation guarantee.
What if it doesn't converge?
So if the function is submodular, it is guaranteed to converge. And if the function is not submodular, it may not converge. In this case, you may set maximum number of iterations, maybe 1,000 iterations. Okay? Yeah. So unfortunately, just like a neural network, okay? Neural network neural network is not guaranteed to always converge, right? Yeah. Because neural network is non-convex optimization. It's not guaranteed to always convert to a stable solution. Okay? Same as here. You can think about submodular optimization. Submodular optimization is just like a convex optimization in numerical domain. Okay? It just guarantees. But if for non-convex or non-submodular, then it becomes theoretical algorithm. But again, even it does not have a guarantee, it works well in practice. Okay? Just like deep learning, it applies statistical gradient descent. Statistical version of gradient descent. And it works well in practice, even it is not guaranteed theoretically to converge. Very good question. Any other question? So I'm going to show you a very interesting theory. So if F is monotone, submodular, and F is that is 0. So monotone, what does monotone mean? So if the size increase, no matter how increase, what item increase, the score always increase. Okay? Just like the flight, right? So given two cities, you add any city, I don't care what city you add, right? It always increase. The only difference is different cities, the increased value is different. So this is monotone. If these three conditions are satisfied, then greedy algorithm return a solution that achieves Fs greater than or equal to 1 minus e over exponential OBT. OBT is optimal. Okay? So what's OBT? Is S star. S star is a global optimal. So this is the mathematical theoretical guarantee of greedy algorithm for submodular maximization. So this is, this bound is called a worst case bound. So what's the case? So which means you can design the function f in whatever way to make the solution as bad as possible. The worst case still is 1 minus 1 over epsilon. Okay? Exponent is exponential value, you know, right? 3.1415, something like that. Okay? So this is mathematical guarantee. So that's why we have so usually say it's a factor 1 minus e of t, a guarantee. I think it's above 2 over 3, right? Above 2 over 3. Because the exponential is above 3, right? 3.1415. Okay? And again, and mathematicians also prove. If we do not assume any specific form for function f, so which means if function f can be any function, it is impossible that you can design algorithm that can be better than this bound. The mathematical proof is impossible. Okay? So which is this is the best algorithm that we can achieve such a guarantee. So please write down, this is very important, and make sure in the future, you can explain this to other people. Right? And then you ask me what is the guarantee for algorithm, right? So algorithm has the same guarantee like this one. Then you ask me, we have two algorithms that have same guarantees. Which one should I use, right? So for this kind of algorithm, right? So we don't have any constraint, but we have either we have no constraint, or we have a simple constraint like size constraint, right? Then both algorithms are fine. But however, for more complicated cases, algorithm can be easily adapted, but a greedy algorithm cannot. So let me give you an example. So far, you know how to solve this problem, right? Max S 0, 1, F must be submodular, right? So you know, I mean, you can return a solution in linear time. The solution has bound 1/1, has a guarantee is 1 minus 1 over e, as good as 1 minus 1 over e, right? So which means it can achieve as at least 2 over 3 your maximum value that you can for your problem. And then you know S01 Fs subject to some budget, right? But how about this problem? Subject to GS B. So which means, so this submodular, this is submodular. So what could be, again, you can easily find many applications. But I mean, I will share some papers with you so you know what are the applications. So if you want to maximize a submodule function and subject to another submodule function must be greater than